All right, so next order of business is to talk about the mean value theorem. All right. All right. At first glance, this theorem may seem yet again like one of those stupid theorems, and I would like to give my dearest apologies for portraying it as such yesterday. All right. Although it's self-explanatory, the importance and the consequences of this theorem cannot be overstated. All right. We're going to use this theorem a lot when we talk about integrals. All right. So even though it's super self-explanatory, it's important. So we got to understand it. Once we read and understand the theorem, let's see why the conditions for the theorem must be met, or else the theorem may fail. So I'm going to explain it, and then I'll go back to this definition.
Okay.
Cool. All right. So the mean value theorem states, right, if you have some function that is defined between 2 points, all right, and you connect those 2 points, right, you draw the secant line between those 2 points. Remember that term? Right. The theorem says that at least one point on the function in between the 2 points, all right, the derivative there will be equal to the slope of the secant line.
Yeah.
So notice how for this function that happens here, happens here, happens here, and happens here, right? But all the mean value theorem is saying that if you look at a function in between 2 points, all right, and calculate the slope of the secant line between the two of them, then there will exist at least one point between those 2 points on the function that will have the same slope as the secant line.
Yeah.
And the way I like to explain it is there's 4 possibilities, right, when you have 2 points, right? Here's the secant line between them. The function has 3 choices. It could either start by going above the secant line, right?
Yeah.
It could start by going below the secant line, or it could travel along the secant line. And we'll show that's the 3 choices that the function has to do, right? It only has the 3 choices.
Yeah.
Would you agree?
Yeah.
Cool. So if it travels along the secant line first, well, then the derivative here is just equal to the slope of the secant line, right?
So it's just every point. Yeah.
Yep. If it travels upwards first, in order for it to make it to this point, it has to curve downwards, right?
Yep.
So if it's going to curve downwards, that means at least one point, its slope is going to be equal to the secant line because it has to curve downwards.
Yeah.
Same here. If it goes down, it's going to have to curve up to meet the point. So then at least one point, it's going to have the same slope as the secant line if it's going to curve back up.
Yeah.
So that's basically the intuition behind the mean value theorem.
Okay.
There are 2 conditions, though. The function has to be differentiable, and it has to be continuous. All right?
That makes sense.
For example, the absolute value function is continuous but not differentiable.
Yeah.
If I take 2 points and I draw their secant line between them, there is no point in between them that has the same derivative as this slope. Would you agree?
Yeah.
Cool. So as you can see, because the function is not differentiable between the 2 points at every single point, then the theorem will fail. And there's no leeway at all. Even if it's not differentiable at just 1 point, the theorem might fail.
Yeah.
It's continuous everywhere and only not differentiable at 1 point, the theorem fails.
Yep.
All right. And yet again, if it's not continuous, then it's not differentiable there. So, we'd have a problem.
Yeah.
Okay. So how are you feeling with that idea so far?
I'm feeling very good with it.
Cool. All right. So let's go and see how the textbook defines the theorem. All right. It says if a function is continuous at every point on the closed interval and differentiable at every point on the open interval, that's basically what I said. It has to be continuous and differentiable. Then there is at least one point in between the 2 points where the derivative there is equal to the slope of the secant line.
Okay.
That's what it says. You see how this is just the slope of the secant line?
Yeah.
And this is the derivative at some point in between A and B. We say C is just some random point in between A and B, and we know that there's at least going to be one point, C, where this is true, where the derivative there is equal to the slope of the secant line.
Okay, perfect.
That's what it's saying. We good with that?
Absolutely, yeah.
All right, an existence theorem. It's important to wrap our heads around exactly what the mean value theorem tells us. As a result, we have to understand that the mean value theorem is an existence theorem. What I mean by that is this. It tells us that there exists a point where the derivative there is equal to the slope of the secant line, but it does not tell us how to find it or where exactly it is. It doesn't tell us where it is, how to find it. It just tells us that such a point exists.
Mhm.
Because it only tells us the point's existence, we call it an existence theorem. Go figure.
Okay.
Cool? So I just want you to realize that the mean value theorem does not tell us how to find this point. It just tells us that such a point exists.
Yes. Okay.
Okay, cool. Applications of the mean value theorem. All right. If the slope of the secant line between 2 points is the average rate of change of the function between those 2 points, remember we talked about that before?
Yeah.
The mean value theorem tells us that the instantaneous rate of change at some point between those 2 points will be equal to the average rate of change. That's all it's saying. If we think about cars, this makes perfect sense, and I'll do a very quick car example.
Okay.
Right? If we want to find the average velocity of a car, right, we take the total distance divided by the total time, right?
Mhm.
Right? And that'll tell us our average velocity between the 2 points, right?
Yeah.
So that's the average rate of change between those 2 points, right? The mean value theorem says that the path that our car actually took, however fast our car was actually going, there will be at least one time where the car's velocity is equal to its average rate of change, which makes sense. If it starts going slower than the average velocity, it's going to have to speed up to make sure that it gets to the end point at the same time that the car would have gone if it was going its average speed the whole time, right?
Okay. Yep. Yeah,
So if it has to speed up, then it'll have to eventually get faster than the car's average velocity because it has to catch up to it, right?
Yeah.
So at one point in between these two, when it's speeding up, its velocity will be equal to the average velocity.
Yes. Okay.
Same here. If it starts going faster, it can't get there before the car would have gotten there at its average velocity, right?
It needs to slow down.
Exactly. And has to slow down so that this car is going faster, right? So in the process of slowing down, at least one point, its velocity is going to be equal to the average velocity. So when we think of average rate of change, yet again, the real life example of rate of change is velocity, right? The mean value theorem tells us that that your instantaneous rate of change, or which we can think of as velocity when we're talking about cars, is going to be equal to your average rate of change at least one point in time, or at least one point.
Yeah.
So this is basically like a real world application of the mean value theorem. We good with that?
Yes.
Cool. And yet again, this says the mean value theorem tells us that the instantaneous rate of change at some point between those 2 points will be equal to the average rate of change. If you think about cars, this makes perfect sense. That's what I just outlined. We feeling good?
Perfect. Feeling great.
Awesome. All right. This is pretty self-explanatory. I don't even know if I'll go in Desmos for this. I'll just explain the textbook definitions. Increasing and decreasing functions. If a function is defined on an interval, defined between 2 points, all right? And we take x sub 1 and x sub 2. They're just 2 points on that interval, all right? If x2 is greater than x1, meaning the x2 coordinate is to the right of the x1 coordinate, all right?
Yep.
And the function value of x2 is greater than the function value of x1, then the function's increasing on that interval. It makes sense, right?
Yeah.
Same with the other way around. If x2 is bigger than x1 to the right of x1, and the function value at x2 is less than the function value at x1, then the function is decreasing on that interval.
Yeah.
Does that sound self-explanatory?
That's super self-explanatory.
Cool. All right, cool. This is another theorem. If the function is continuous and differentiable on the interval, if the derivative is always greater than 0, then the function's increasing on the interval. That's pretty self-explanatory, right?
Yep.
If the slope is greater than 0 always, then of course it's going to be increasing.
Yeah.
If the slope is less than 0 always, of course it's going to be decreasing on that interval.
Yeah, exactly. I'm kind of surprised they put these even in the textbook.
Yeah, it's just like like I agree, but in math it's important to like have everything written down as rules, so we're not assuming. Yeah, so we're not assuming anything. So I think that's
better
what
to like include too much versus not include enough.
Yeah, so I could omit these, but I might as well include them because the textbook includes them, and just to show you that it's still important to make sure that we write down the things that are intuitive to us so that we can use them legitimately.
Yep.
We don't want to be assuming anything, so we got to put them down on paper.
For sure.
Okay. These two theorems, feeling good, right?
Yes.
Cool. So 2 more slides. Almost done. All right. Here's we're getting into a sneak peek to Unit 5, which they introduced in this unit, and I might as well just talk about it very quickly. If the general derivative of a function is 0, right, then the original function is a constant function, right?
Okay.
If we get the derivative of a function is equal to 0, then the original function has to be y equals some number, because that's the only function that exists where the derivative is 0 everywhere.
Yeah.
You agree with that?
Yes.
So it basically says the only functions with a derivative of zero always are constant functions where y equals a number.
Okay.
So the emphasis here is that these are the only functions with the 0 derivative. No other function exists, which makes sense. And when we say the 0 derivative, we mean the general 0 derivative, as in the slope is 0 everywhere.
Yeah. Okay.
That makes sense?
Yep.
And you can also see why no other function would meet that property, because if the slope is going to be 0 everywhere, it has to be a flat line.
Yes.
Cool. Additionally, if we have the derivative of a function and wish to find the original function, we don't have enough information. All right. Here's why.
Yeah.
I think I explained this yesterday. Let's say I found that the derivative of an original function was 2x. And I wanted to find what is the original function, right? You might be like, oh, well, Dylan, is x squared, right?
Yeah.
But what if I made the function x squared plus 1?
Yeah, then it's still...
Or x squared plus 2?
Yeah, exactly.
Or 3, etc. It still has this as its derivative. So you want to do a sneak? We can do a sneak peek to differential equations, right? If we have a differential equation like this, right, dy over dx equals 2x, right, there is no definitive solution.
Okay.
All right, because infinitely many functions have this property where its derivative is 2x.
Yeah.
And they all differ by just a constant. So all of the functions with this property will look like this: x squared plus some number. So when I say they all differ by a constant, you see what I mean, right?
Absolutely, yeah.
Cool. So when we get into differential equations, we're going to be talking about it, but the general solution to this differential equation would be this. And we include c to let it know that it can be any function that differs by just a number.
Okay, cool. Yeah, no, that makes sense.
So that's a sneak peek to differential equations. So, you know, you're already acing it. Cool. All right. Yep. However, if we were given like an initial condition, for example, so if, for example, let's say we were told that we're trying to find some function with this derivative, all right, and the function was equal to 4 at x equals 2.
Yep.
When we're given this condition, we can then pinpoint the exact function, right?
Yeah.
Because only one of these functions will have this property, and that's x squared.
Yep.
So even though infinitely many functions have this property, only one function will have this property and this property.
For sure.
Right? So we can solve a differential equation if we have an initial condition, which we call this initial condition. So that's a sneak peek. All right, cool. All right. Above, we were given a derivative and asked to find the original function. In general, if we have a function and we're asked to find a function whose derivative is the original function, that's a mouthful, but you kind of get what I'm saying?
Wait.
Yeah. If we have a function and we're asked to find another function where if you differentiated that new function, you get the original function.
Yep.
All right. The function we find would be the antiderivative of the original function. Does that make sense? Because you're anti-differentiating, you're backtracking. Instead of taking the derivative, you're finding a function that has that function as a derivative. Yep. You're doing the backwards process. In general, if you have a function f, then g is an antiderivative if the derivative of g is f of x.
Okay.
Does that make sense?
Yeah.
All right. The process of finding an antiderivative is anti-differentiation. Go figure. And with what we have outlined, a function has infinitely many antiderivatives. And more on that in Unit 5 and 6. So hopefully that makes you as excited as I am.
Oh, I'm excited.
Cool. All right. If two functions have the same derivative, then they differ only by a constant. And this is true. If two functions have the same derivative, then they have to be the same function but only differing by a number.
So that's what you were like just saying, like 2x plus c.
Yeah, exactly. So I don't know what the hell I'm doing. And I'll explain it just so we like very quickly, just so it's intuitive. If I had two functions that had the same slope, right? So here's a function, right? If I wanted to make another function that has the same slope as this function at every point, the only possible functions I can make are vertical translations of that function. No other function will have the same slope as this unless it is the same function, either moved up or down or on top of it.
Yeah.
So it's basically, it's not just saying.
Also move it horizontally, right?
Yes, but remember, if you move it horizontally, then the derivative at a point x will be different. Right?
Yeah, okay.
Here's a horizontal translation. Here the slope is like positive, but here the slope is very positive, so they're different.
Yep. Yeah, absolutely.
So that's why only vertical translations work.
Okay. Yeah.
Even though they look the same, they're different because they have. If we said these functions would not have the same derivative function.
Yeah.
Because the derivatives are different at the x coordinates. All this is saying that if functions have the same derivative, then they have to be the same function, only differing by a constant.
Okay. That makes perfect sense.
Yep. And it's just saying that these are the only functions that exist. It's really stupid. It's just saying no other function exists. If you had two functions with the same derivative, then you can't find some other weird function with that property. They have to be the same thing, only up or down.
Okay. Yep.
Which I hope makes sense.
Perfect.
So that's the emphasis. It's not just saying that they exist. It's saying they're the only functions that exist with the property.
Yeah.
And yet again, this is because two functions cannot have the same slope everywhere without looking identical to each other, right?
Mm-hmm.
Hence, they must be the same function, but translated up or down. They can't have the same slope unless they look exactly the same.
Yeah.
Okay. Also, the antiderivatives of a function we find using the method outlined before are the only antiderivatives that exist for a function. That is, no other functions whose derivative is the original function that aren't the antiderivatives we would have calculated from the previous methods. Yeah, to Jamboard to see. Okay. I don't know if I have to go to Jamboard to explain this. I'll explain it slowly. It's basically just what we said before applied. If two functions have the same derivative, right? They must be the same function, but translations of one another.
Yep.
Which means that the only antiderivatives of a function that exist, all right, are the family of functions we found, right? The x squared plus c. Those are the only antiderivatives that exist for x squared. No other weird, even if we define a super weird function, no other function would exist that would have the derivative of 2x. It has to be in the form of x squared plus c.
Cool.
That's all it's saying. It's saying no other family of the only antiderivatives of 2x are x squared plus c. No other function exists with that property.
Yep.
And does that kind of make sense?
That definitely makes sense. Yeah.
Cool. All right. So with that, that's all for today.
All right.
Tomorrow we continue our discussion on applications of derivatives. We will discuss the connection between the graphs of a function, the graph of its derivative function, and the graph of its second derivative function. We'll talk about how we can get information of the original function if we see the graph of its derivative and the graph of its second derivative. We'll talk about optimization and modeling with derivatives, which is a callback to what we talked about with absolute extrema. Because obviously, if our function is like how much money we're going to make, then we want to make the most money. So that's going to occur when our function is at the absolute maximum. So obviously, modeling and optimization is going to come back to what we talked about today. So that's cool.
Okay.
By the way, we have covered over 200 pages of the textbook as of today. Pat yourself on the back. I cannot express how proud I am of your hard work so far, and I hope you keep keeping it up because I'm super impressed.
Oh, that's huge.
It is huge. So we're doing a great job.
Pat yourself on the back too.
Thank you. It really, like, I can teach it, but I already know it. You learning it is, and you doing as good a job as you are is cannot be overstated how amazing of a job you're doing.
Okay, you too.
Okay, so we just covered a third of Unit 4.
Word.
There's my animation for the day. Have an amazing day. So I'm gonna end the video, and then we'll go into Zoom and we'll wrap up our final thoughts.
Yeah.
All right. Thanks for watching, guys. See you in the next video where we talk about what I just outlined.